In this lesson, we are going to look at sections 4 and 5 of chapter 1. In section 1.4, we are going to look at the marginal distributions. Marginal distributions are the density functions of x alone or y alone when x and y are jointly distributed. Definition 1.4. Marginal probability mass functions. Let x and y be two discrete random variables with the joint PMF Pxy. Then the marginal PMF of x can be obtained by summing up the joint PMF over y, while the marginal density of y can be obtained by summing up the joint PMF over all x. We can define the marginal densities for the continuous case as follows. In the continuous case, the marginal distribution of x, that is fx, can be obtained by integrating the joint PDF over y, while the marginal density of y, which is fy, can be obtained by integrating the joint PDF over all x. Let's look at an example. The joint PMF of two discrete random variables x and y is given as follows. X can contain three values 0, 1 and 2, whereas y also can contain values 0, 1 and 2. If you want to check whether this is a valid joint PMF, you can add up all probabilities. There are 9 possible outcomes. You can add these probabilities and check whether they add up to 1, and it is true in this case. Now let's find the marginal PMFs of x and y. To find the PMF of x, we add all the probabilities of y for x equals 0, x equals 1 and x equals 2. That is the row sum. For example, when x is 0, we add up all values for y equals 0, y equals 1 and y equals 2. That is 1 over 9 plus 2 over 9 plus 1 over 9. So when x equals 0, the probability of x is 4 over 9 by adding up all values of y. We do the same for x equals 1 and also for x equals 2. So the row sums of this table will give the marginal distribution of x. If we follow the same calculation column-wise, you can find the marginal density of y. When y is 0, you add up all probabilities when x equals 0, 1 and 2 together, which will end up 4 over 9, and do the same when y equals 1 and y equals 2. So the column sums will give you 4 over 9, 4 over 9 and 1 over 9. Now let's look at a continuous case. Here is the joint PDF of x and y. Let's find the marginal distribution of x first. To find fx, we integrate the joint density with respect to the other variable, which is y. The support of y is from 0 to 1, so we integrate the joint PDF from 0 to 1. And we can get the answer 4x over 5 plus 3 over 5. The support of x is from 0 to 1. Now we do the calculation for y. The marginal distribution of y can be obtained by integrating the joint PDF over the other variable, which is x. Since the support of x is from 0 to 1, we do the integration x from 0 to 1. And the answer will be 2 over 5 plus 6y over 5. Again, the support of y is from 0 to 1. Let's look at another example. Can you find the marginal PDFs of x and y for the following joint PDF? Is this a valid joint PDF? In this example, the support of x and y are depending on each other. Therefore, this example is different from previous examples. The support of x is from 0 to y, where the support of y is from x to 1. Hence, x and y are depending on each other. We have to consider this carefully when we do the integration. Let us first check whether this is a valid joint PDF. We integrate the joint PDF first by y. The support of y is from x to 1. And then we integrate x from 0 to 1. Remember that since we have already taken care of the variable y, we integrate x from 0 to 1. If we do this integration, you will end up with the total probability 1. Hence, this is a valid joint PDF. Now let us find the marginal densities. The marginal distribution of x can be obtained by integrating the joint PDF with respect to y. Since the support of y is from x to 1, we integrate y equals x to 1. And we can get the answer 2 times x minus x. Now we do the same calculation for the marginal density of y by integrating the joint PDF with respect to x. Remember, support of x is from 0 to 1 and the answer will be 2y. Here are the marginal distributions of x and y. Section 1.5 Conditional Probability Distribution. The probability distribution of variables can be conditioned on other variables. The idea of conditional probability can be extended to conditional probability distributions. Given two jointly distributed random variables x and y, the conditional probability distribution of y given x, denoted as y given x, is the probability distribution of y when x is known to be a particular value. Definition 1.6. Conditional probability distribution function of a discrete random variable. Suppose you have two discrete random variables x and y and their joint PMF pxy and the marginal PMFs px and py respectively. Then the conditional PMF of x given y equals a value y is the division of the joint PMF over the given condition. The given condition is the probability of y. Similarly, the conditional PMF of y given x equals a certain value x can be obtained by dividing the joint PMF over the given value, that is px. In both situations, the denominator should exceed 0 to avoid any divisions by zeros. Now let's define for the continuous situation. Let x and y be two continuous random variables with the joint PDF fxy and the marginal PDFs fx and fy respectively. Then the conditional PDF of x given y equals y can be obtained by dividing the joint PDF fxy over the given probability, that is fy, or 0 otherwise. By interchanging the values of x and y, you can find the conditional PDF of y given x. Note that conditional PMFs and conditional PDFs are genuine probability distributions. Let's look at the example 1.4 again. We already have the marginal PMFs of Px and Py. Let's try to find the conditional probability of x given y equals 1. We apply the definition, that is, the probability of the joint PMF x, 1, because we already know y equals 1, that is the given condition, and we divide by the given value py equals 1. Since the probability y equals 1 is 4/9 from the PMF, we can apply that value for the denominator straight away. But for the numerator, x can contain 3 possible values, that is x equals 0, 1 or 2. Hence, we do the calculation for all 3 values separately. When x is 0, the probability that x given y equals 1 will be the probability of the cell 0, 1, which is 2/9, divided by the condition 4/9. So the answer will be 1/2. We follow the same calculation when x is 1 and also when x is 2. Now we can rewrite these probabilities as a table. If we add up these probabilities, they will add up to 1, showing that Px given y equals 1 is a valid PMF. Let us look at the joint PDF in example 1.6. What is the conditional density of x given y for any value y? Since we already have the marginal density of y, that is the given condition, we can calculate the probability of x given y using the same equation. Applying the values we already found in example 1.6 in this equation, you can find the conditional density of x given y. And it will be 1/y, and remember the support of x is now from 0 to y. Now you can use this conditional PDF to calculate the probability for any value y. Let's say we need the conditional density of x given y equals 1/3. What you have to do is simply substitute the value 1/3 in your equation of conditional probability. So your answer will be 3. If you want to double check your answer, you can always integrate this value over the support 0 to 1/3 and show that it is 1.